ICAMIS inspection.
Ah.
So there is a 6-member committee is there. Everybody is completely engaged, and classes are going on, exams are going on, and this conference is going on. So there is a less workforce.
Correct, correct. So you have some poster session also, right?
Yes, sir. Presentation session is there. After your presentation, we will go to the Google Classrooms. So we will divided the 3 classrooms, and the participants, they will go to the respective classroom and they will present the presentations.
Okay. हेलो हेलो कहाँ से हाँ नहीं सॉरी आई एम बिजी आई विल कॉल बैक लेटर
is the most powerful weapon which you can use to change the world. Believing in this principle, welcome to Murray Lakshman Reddy Group of Institutions, providing world-class education and research facilities to help transform people's lives for the better. It is the brainchild of a visionary who conceived and promoted it in 2005. Meet the man, Sri Murray Lakshman Reddy, who ushered in the silent mission. A mission to provide technological advancement from time to time, with the aim of imparting education with global standards to enrich values with knowledge in students. Succeeding the paths of Sri Marri Lakshman Reddy, making education a positive experience. Sri Marri Rajashekhara Reddy, Founder Secretary, nurtured MLR group of institutions to win the pride of being recognized as one among top engineering colleges in Telangana for the past consecutive academic years. Situated in vast and peaceful area of 35 acres, students here tend to learn experimenting their live projects through centers of excellence, which is tied up with various industries. Spacious and comfortable classrooms, corridors, advanced laboratories, with equipped ultra-modern audio-visual technology auditorium, accommodating 1,000 plus audience, separate hostels for boys and girls. Each student is specially taken care for the provision of health facilities and hygienic food in spacious and eco-friendly canteen, etc. are salient features of MLR group of institutions. AICTE recognized MLR group of institutions accredited by NAC with A grade and has NBA accreditation for all programs. MLR Sports Complex and inaugurated by MLR group of institutions with most advanced multi-sports facilities like cricket stadium, badminton court, table tennis, billiards and basketball, etc. MLR Sports Complex organizes many national and international university-level sports fests by grooming every aspirant in competing national and international sports forums. Successfully achieved 50 gold medals, 13 silver medals and 16 bronze medals at various national and international sports events. MLR Group providing free admissions every year by supporting aspirant under sports quota with scholarships for the meritorious sportspersons to pursue their career in sports and opportunities in government sectors. To sharpen and extricate students' creativity and entrepreneurial skills, MLR Group has established Center for Innovation and Entrepreneurship with facilities like Social Square, Innovation Hub and Makerspace. The Makerspace is a technical prototyping platform for students' innovation and invention, which is loaded with ultra-modern equipments such as multimedia workstations, 3D printers, CNC machines, laser cutters, and thus provides stimulus for student entrepreneurs. The center has collaboration with various government and non-government ministries for raising seed fund to incubate student projects and startups. This center has developed 8+ market-ready products and supported 11+ student startups. MLR Group has set up livelihood business incubation in association with Ministry of Micro, Small and Medium Enterprise (MSME) to promote new technology or livelihood-based enterprises. Research and Development Cell has 12 centers of excellence in association with various industries and supports faculty and student research. It also has a track record of 25+ funded projects, 700+ SCI or Scopus Journal articles and 35+ intellectual property rights, and the progress continues. In preparing the aspirants to the real-world competitiveness, MLR Group of Institutions has introduced Indo-Universe Collaboration for Engineering Education IUCEE to introduce outcome-based student-centric education and Bloom's taxonomy-based teaching, learning and evaluation process, engineering projects in community services (EPICS) in association with Purdue University, USA. Scope: School of Programming Practices to hone the coding and programming skills. students' platform for engineering education development, SPEED, empowers the students to become a factor of change in engineering education and its effect on society and environment. Club Literary to organize MUN, TEDx Talks and Techno-Cultural Fest to uplift student communication and English skills to the global forum. MLR Library is fully loaded with diversified study material, books, national and international journals with dedicated digital library along online subscription to massive open online courses, IEEE, Elsevier, Springer, ACM journals, etc. MLR assures the safety and security of the students. Its transport infrastructure includes modern and secure vehicles and strictly complied with RTA regulations with well-maintained safety standards. MLR group of institutions having faculty of nationwide experienced and renowned adjunct professors include the expert scientists of DRDO, DRDL, HAL, BHEL, SAE India, ECIL and JNTU, imparts education with pure practical inputs, offers courses in BTech, Aeronautical Engineering, Computer Science Engineering, Civil Engineering, Electronics and Communication Engineering, Electrical and Electronics Engineering, Information Technology, Mechanical Engineering, MTech with Aerospace Engineering, Computer Science Engineering, Embedded Systems, Digital Systems and Computer Electronics, CAD or CAM Engineering, Thermal Engineering, MBA courses. MLR proudly announces that till now, 75% of their students have grabbed the opportunities with average salary package of 6 lakh by holding premier positions in top-notch companies in global market. MLR relies always on the philosophy that intelligence plus character. This is the goal of education.
Good morning, Professor Surajit Dara and all the participants. I welcome you to the International Conference on Advanced Materials for Innovation and Sustainability organized by the Department of Science and Humanities, MLR Institute of Technology. Thank you for joining us. Dr. Surajit Dara is currently working as a professor at University of Hyderabad, Central University, Hyderabad. He did his PhD from Raman Research Institute in 2003. After that, he joined Department of Organic and Polymeric Materials, Tokyo Institute of Technology for the postdoctoral studies. After that, he immediately joined the School of Physics at University of Hyderabad in 2006. He is one of the experts in our country in soft condensed matter. So his research interest includes phase transitions, structure property correlation of liquid crystals, topological defects, directed self-assembly of colloids in liquid crystals, electrokinetics of colloids in liquid crystals, optical resonance and lasing in liquid crystal microdroplets, rheology of liquid crystal, colloids, polymers, gels, and ferrofluids. For his contribution to the scientific community, recognized by the Government of India, awarded with the Shanti Swarup Bhatnagar Award given by the CSIR. Similarly, for his contribution recognized by the Department of Science and Technology, awarded him with the Swarna Jayanti Fellowship in 2016. For his contribution, N.S. Satyamurthy Memorial Award in Physics for Young Scientist in 2012. For his contribution, International Society recognized his contribution to the community and awarded him with the Michi Prize in 2010. He has published more than 100 papers in peer-reviewed journals and he guided more than 10 students and still is guiding another 6 students. So is today is our guest and keynote speaker is going to deliver about the colloids in liquid crystals. Thank you, Professor, joining us. Now take over this session. Over to you. Thank you very much.
Thank you, Professor Arun, for the invitation. And also, I would like to thank the conveners for this conference. And so let me first share the screen. So is it clear, visible?
Yes, sir. Yes, sir. It is visible.
Okay. Okay. I'm going to talk about smart and active materials based on liquid crystals. So I think most of us are familiar with the terminology liquid crystals because most of the flat panel displays which we use in our daily lives, like computers, laptops, mobile phones, even watches, even all kinds of non-emissive displays which you see around are mostly made of liquid crystals. So therefore, liquid crystals are sort of integral part of our daily lives. Okay. Now, today I will try to present some new aspects of liquid crystals, which is being pursued in the recent years. And these results are from our group. So this talk, I will have two parts. In the first part, I will present the directed assembly of colloids in liquid crystals, meaning that I will show you that unlike the colloidal interactions in isotopic solvent like water, we have very unusual self-assembled structures of particles, microparticles in liquid crystals, and that helps us to make smart materials. Okay, and in the second part, I'll show you that when you apply external electric fields to these particles in liquid crystals, they become micro swimmers, and their swimming mechanism is somewhat sort of similar to those we see in living systems like a living microorganism like bacteria or even the algae. Okay, so finally, of course, I will conclude my. So this the first part of the work was done by the four students, Zuhail, Junaid, Devika, and Rasi. And Junaid is present in Kalika University. He is working as assistant professor. Junaid is the University of Leeds, and Devika and Rasi are the present students. In fact, Rasi just submitted the thesis. And the second part of the work was done by another student, Dinesh Kumar Sahu. The experiment was done by Dinesh Kumar Sahu, and the theoretical part of the work was done in collaboration with Sriram Ramaswamy and his student Swapnil Kole from Indian Institute of Science, Bangalore. And of course, most of this research work is research works are done with the help of funding from the Department of Science and Technology. So let me give you some brief introduction to the liquid crystals. Liquid crystals are sort of made of organic molecules, organic shape and acyclic molecules, like which you see some of them are here. And for example, the molecules can have a rod shape like this. It can be a bend shape, or also it can be a disc-like molecules. Okay. So what is important is to have a liquid crystal phase is that, of course, one is the organic molecules, and secondly, these molecules must have shape anisotropy, meaning that like their length should be larger than their effective diameter, or shape asymmetry like this. And in fact, these disc-like molecules or the liquid crystals were discovered more than 40 years ago in India at Raman Research Institute, Bangalore. So liquid crystals, they exhibit varieties of phases. And for example, if you have rod-like molecules like this, so this is one of the examples of rod-like molecules. The rod-like molecules, on an average, they tend to align in some directions, okay, like this. So what you can see, the center of mass of the molecules are random, but on an average, their axes tend to align in some direction, and that direction we define as a director, okay. So and which is represented by N. And since there is no head and tail, N and they are equivalent. And please note that this symbol I will be using again and again in my talk. So the N means the average orientation direction of the molecules. Now, depending upon this molecular structure, if you decrease the change or change the temperature, it so happens often that this molecule tend to segregate in a layer like this. So this is sort of a layer or lamellar structures. And so the difference is that with respect to this, apart from the orientation and order of the molecules, additionally, they have one-dimensional periodicity of density in this direction. Okay, and this is called smectic, and this phase is called nematic. And and if these molecules are tilted with respect to the layer normal like this by angle theta, then this is called smectic C. In fact, I have simply introduced 3 liquid crystal phases which are used or studied extensively, but the phase which is used in most of the liquid crystal displays is the nematic phase. Okay, there are more than 40 such phases are known. In fact, still now new phases are being discovered. Okay. Now, as I said, liquid crystals, which simply means that they have some properties like conventional liquid, and they also have some properties of like conventional crystals. Let us briefly see what are the physical properties crystal-like and what are the properties liquid-like. One of the things we should sort of recognize is that liquid crystals are basically ordered fluids, meaning the long axis of the molecules are ordered, and that order can be quantified with a second-rank order parameter Q alpha beta, which is given by this expression. But AS is this basically kind of on a scalar order parameter, which is basically a linear polynomial P2 cos theta. Okay. Now the N is the director. If you recall, I said in the previous slide that N is the director, and alpha beta means this quantity is in the first bracket. Basically tells you that yes, it's a fluid phase. So S is the basically magnitude of this scalar order parameter, and this part takes care of when it hits the fluid, they can change the direction in the medium. Now, since the order parameter is second rank tensor, the consequence is very simple, that this most of the physical properties like dielectric constant, conductivity, stress, elasticity, they are also second rank tensors. Therefore, they are represented in this form. Now, if the medium is a uniaxial nematic and having cylindrical symmetry, okay, so uniaxial nematics means they have cylindrical symmetry. That means they have 2 effective length scale. One is along the long axis or along the director, and another axis is the perpendicular to the director. Now, since there is a 2 different directions, so we get what is called the optical anisotropy of the birefringence, which is defined as delta n. That is the refractive index difference along the long axis with respect to the perpendicular axis. Okay. As this refractive index is the properties of crystal, we should recall that the refractive index is the properties of the crystal. Similarly, the dielectric anisotropy also you can have essentially 2 quantities, that is dielectric constant along the long axis or the director, and another is the perpendicular, and difference is this called dielectric anisotropy. Similarly, you can have conductivity anisotropy, delta sigma. It is please note that the liquid crystals are usually dielectric, but since it is organic material, some amount of impurity ions are always present. That gives, and those ions actually move under the external field. Therefore, they give rise to anisotropy in the conductivity. Okay, and this is the origin of the conductivity in liquid crystal. Another important aspect is that the elasticity, like crystals. Remember that this. I mean, I think all of you know that these liquids do not have elasticity. Right? They have viscosity. But since the liquid crystals, apart from the viscosity, they also have elasticity, and this elasticity is called curvature elasticity, meaning that if you have a uniform orientation of these molecules, it doesn't cost any elastic energy, but it is easy to form elastic deformation like splay. You can see non-zero divergence of the molecules, and you can have a twist or you can have bend of this molecular axis, orientational axis. These kind of structures cost elastic energy, and they can be represented by this equation. What is important to note that if you want to create this kind of deformation from the uniform state of the liquid crystal, it costs elastic energy, and they are called splay, twist, or bend, which is obvious from this schematic diagram why they are called so. And if you look at this order of magnitude of this elastic constant, splay, twist, bend, it is 10 to the power minus 12 Newton, extremely small, much smaller than the elasticity of solids, which you know. That is why these liquid crystals, they belong to materials called soft materials. Means we can easily deform the state of the material by applying external perturbation. Now, like solid crystals, you have a dislocations. Liquid crystals also have defects, and they are called disclination. So if you take a liquid crystal sample between two glass slides and look through an optical microscope between two cross polarizers, because this is a birefringent medium, we can see the very colorful textures. These are called textures, and the color comes because of the birefringence. If the sample birefringence is 0, we will see complete dark. Okay. Now, what is important thing to notice is that there are dark lines moving here and there. Those line regions means these regions actually means the director or the optical axis of the liquid crystal is either parallel to analyzer or polarizers. That is why they are dark. But apart from that, there are some regions where 4 dark lines are meeting. Okay, like these, and these points are called defects. So defects, what are defects? Defects are basically the discontinuities in the director field. Now let us closely look at what is the structure of this molecular orientation, or what is the orientation of the molecules around a defect. For example, this is a point defect, and the defects can be have strength like in solid dislocation crystals, like dislocation. In case of liquid crystal, it is defined as the M, that is alpha by 2 pi, which means if I rotate around this point defect, around this point 2 pi, how much angle the molecules rotate? For example, in this picture, if I rotate by 2 pi, we can see that these molecules also rotate 2 pi. Therefore, alpha is 2 pi. That means M is 1. So this defects. So this is the structure of this +1 defect. Means that this is called radial hedgehog. This means that from this point, the liquid crystal molecules are sort of coming out. Okay, and this is called radial hedgehog. You can have a hedgehog structure, but with a hyperbolic structure like this. These are called hyperbolic hedgehog. And in this case, we can see when we go clockwise, the director or these lines rotate anti-clockwise. Therefore, this defect is called -1. Okay, sorry. Similarly, we can have also defects of -half or +half. In this case, if we rotate 2 pi around this point, the director rotates only pi. Okay, and sensor rotation is clockwise, therefore it is +half, -half. Therefore, I have simply demonstrated you that some basic structure, the defect structure of liquid crystal, namely +1, -1, +half, -half. Of course, higher strengths of defects are also possible, but that is not easy to stabilize in liquid crystals. But they are available. It's possible. Okay. Now, suppose these defects are in the context of liquid crystal displays. These defects are unwanted, meaning that you do not want any defects in the liquid crystal displays. So you want the entire liquid crystal system should be uniformly aligned. But these defects actually can be created artificially by dispersing some foreign particles, microscopic particles or nanoparticles in the liquid crystals. Okay, and I will show you in this talk that those defects are very useful. And by engineering the defects or defect structure, we can create a large self-assembled colloidal crystals, which are very, very important for the photonic crystal perspective. Now let us see, this is a liquid crystal at room temperature. It's a turbid liquid. You can see white color. If you look at some small part, we can see that this on an average the molecules are oriented in some direction. This is called director, as I said. Now suppose I drop a small particle within this liquid crystal, and so what happens? The liquid crystal molecules get anchored on the particle surface. Therefore, either these molecules can be perpendicular to surface, or the molecules can be parallel to the surface of the particles which you drop here. Now, if they are perpendicular, we can see that they will have a splay structure or splay deformation, elastic deformation. If the molecules are parallel, they will have a bend deformation. What do I want to say here is that by putting a foreign particle, we can create splay or bend like elastic deformation in the liquid crystals. Now, what is interesting consequence of this dispersing microparticles in liquid crystal is that if you look at the elastic energy, which can be written in this fashion, where K is the average elastic constant and N is the divergence, okay, or gradient of this director. Let us say one elastic constant approximation, that is bend, splay all are equal. Now, if you write the elastic energy and assume that this, to begin with, the director or the molecules are oriented in the x direction, therefore Nx is 1. Now, if you minimize this energy, and we get a Laplace equation, and solution of the Laplace equation is given by this. So what is Ni is the director and I is the Y and Z component. What it means, when you drop a foreign particle in liquid crystal, the Y and Z component of a director field somewhat looks like the multiple expansion in electrostatics. Okay, this is due to monopole, this is dipole, and quadrupole. That means when you drop a particle in uniform liquid crystals, the particles act as multipolar sources, somewhat similar to what is known for for the electrostatics. Okay, so see the difference is that this is the elastic distortion of this. Okay, the distortion is of the order of monopole, dipole, and quadrupole. Okay. Now let us see experiment what happens. So when we drop such particles in liquid crystals, so what happens? As I said, they create the elastic distortion, and the elastic energy increases as Kr, where R is the radius of the particle. So the bigger is the particle, the elastic energy is higher. But again, this, let's say W is the surface anchoring energy of the molecules. That means molecules have some anchoring energy on the surface, and then the anchoring energy of the whole system is WR square for a particle. And these two energies, you see, will grow with R, but anchoring energy will go much faster because it is quadratically varying with R. Therefore, there is a competition between these two energies. That two energy will stabilize some defects. What you see in the experiment is that if we drop a spherical particle like this, the molecules are anchored. Therefore, in the far field, the molecules want to tend to be aligned in this direction, but in the local region, they are strongly anchored. Therefore, there is a deformation around the particle. That means as if the particles, the lines are that, or the molecular orientation looks like the particle, there is a +1 defect here, meaning the lines are coming out from the center. Okay, so that means this particle act as a +1 defect. Therefore, topological charge conservation expects that you should have another -1 defect in the vicinity of the particle. This is what this black dot. You can see the director profile around. This is a -1 defect. Therefore, each particle you drop, it creates a pair of -1 defect and one virtual +1 defect, and this structure is called elastic dipole. Okay, this is not electric dipole, it's elastic dipole because this comes from the director configuration of this particle. Now, if you look under a microscope, okay, for a dispersed particle, a single particle, we can see that there is a point defect here, and this direction is this direction of the long axis of the molecules. Okay, that means in this region they are uniformly oriented, but here they induce a defect. If you remove the polarizer or analyzer, we can still see there is a defect point here. Okay, and this is silica particle, of course, of few micron size. And now the elastic dipole, if you want to define the direction, it is from -1 to the +1. Okay, this is elastic dipole. Similarly, these point defects can be sort of compressed, and it can be opened as a ring. So the point defect goes towards the particle, and it open as a ring, and it becomes a ring defect. This looks like a Saturn ring. That is why it is called a Saturn ring defect. Okay, and if you look under a microscope, you can see that there is a clear ring around the particle of around 5 micron size diameter, 5 micrometer, and this is also seen without polarizer. Okay, therefore we can see that these particles with the homeotropic or boundary or perpendicular boundary condition, we can induce a point defect or a ring defect. Okay. Now, if we have two such particles with the point defects, you can see the elastic dipole, and like in electrostatics, two parallel dipoles will repel. Therefore, we can see the potential energy or repulsion is the red one, which is increasing. If there are antiparallel orientation, there will be attraction. You can see that this is potentially attractive. Now, what is important to notice here that the potential energies are few thousand kVt, which is much larger than the small forces the colored experience in water. Okay. Now, in this video, I can show you the two particles. If you leave around, you see slowly, we can see they approach each other because of these elastic attractions. Okay, and this expression gives elastic interaction energy. But please note that when depending upon the angle theta, that is angle between the running line and the approaching of the particle, okay, they could be attractive or repulsive. Okay. Now, similarly, if we have two particles with a ring defect, these are two particles with ring defect, we can see as the time elapses, they tend to merge and form a pair. Okay, and this attractive elastic energy is order of again few thousand kVt. This can be also mathematically expressed by this. The point is that unlike these choroidal interactions which you see in water, they are mostly short range. Yeah? They could be steric, van der Waals, or electrostatic interactions. But that interaction is short range, and you can't do much control on those interactions. But here, when you disperse the particles in liquid crystal, we can actually manipulate the defects as well as the interaction. That means we can have a dipolar interaction or a quadrupolar interactions and many more. Okay. So now, okay, so this is all about these particles that that means the particles, when you disperse in liquid crystal, they induce defect. Now, so what? What is the use of such defects? So these particles, let's say, you can see that spontaneously sometimes tend to form a long chain. This is a chain of 4 particles. If you look at the structure, this line says the molecular orientation. So 2 particles are separated by a defect point here. This is defect here, defect here, defect here. These are all -1 defect. And the elastic distortion or the molecular orientation of the particles is like this. Okay. So they have a long range attractive interaction, but they don't collapse because there are short range forces, repulsive force between these 2 particles because of these point defects between them. Okay. Now, so we can use a laser tweezers, okay, which is a highly or tightly focused laser beam to guide this motion of this particle. This spot is the laser beam, which actually creates some elastic deformation, and we basically trap this particle using the laser beam and guide the small particles under the microscope to form a large sort of or bigger assemblies like this. This is basically a demonstration how a colloidal assembly or colloidal order can be made. So with this idea, I will show you that we can make a defined type of structure. This is a sort of bigger 2-dimensional colloidal crystals. You can see they are perfectly ordered crystals, and these particles are silica particles. They are bound by topological defects, and the structure is quite rigid. The binding energy is of the few thousand kPa. Therefore, the thermal fluctuations cannot break this bonding of these particles. Okay. Now, these liquid particles are made in a liquid crystals, which also has a phase transitions from nematic to symmetric A. Symmetric A is basically a phase where you have an additionally layer structure. Now, if you see in this, when I decrease the temperature, what happens? When I decrease the temperature, you can see the lattice parameter or spacing among these particles tend to increase, and eventually they collapse and form a closed pack structure. Now, I can also heat and get back the original structure where I started. So this is heating. Therefore, I can make a reversible or tunable structure going around the phase transitions of the liquid crystal. This is very, very useful. I'll show you later. So if you see that in the beginning, I had a 2D crystals with a oblique lattice, but as we go to this symmetric A phase, we can have a closed pack like hexagon structure. Okay, and these structures are very useful for making photonic crystals later. Now, the question is again, do we understand why this interparticle separation is changing across the phase transition? I will not go into details, but I will just briefly try to mention that so this is the T minus T Ni. Na is the transition temperature. 0 means this is the phase transition temperature. Above means high temperature phase. Below is a low temperature phase. So above is the nematic, and this is the symmetric phase. Now, so when the 2 particles are there, you decrease the temperature. What we find is that interparticle separation tend to increase. They diverge, then collapse, then again increases. Okay, and this can be understood based on the temperature-dependent elastic constants of this medium. Okay, so I will not go into details, but the point is that the discontinuity in the lattice parameter, what we see, is essentially due to the discontinuity in the elastic constants of the medium across the phase transitions. Okay. So I have shown you that how we make a 2-dimensional colloidal crystals made of dipolar particles, meaning a particles having point defect. Since I said we can also stabilize particles with ring defect, and we can again use laser tweezers to assemble many particles and create some sort of 2-dimensional assembly. Now, what we see is that the symmetry of this crystal is different than a dipolar crystal. Okay, so AB or the lattice parameter, this angle is the gamma. So there are 3 lattice parameters, which is different than the previous crystal. That means the crystal structure depends upon the defect structure of the particles. Okay. Now we can have a defects of -2. That means this is a escape or hyperbolic defect ring, the ring acts as a glue which binds two particles tightly. The binding energy again is very, very strong, and we can see. So basically, this is a dimeric unit. Okay, two particles are joined. Now, using several dimers, we can assemble and then make sort of two-dimensional colored crystals, like as you see here. Okay, this picture is taken between cross polarizers, means optical polarizing microscope. Now, these structures are tunable by temperature again. So, for example, if I change this temperature, okay, you can see that this again lattice parameter tend to change, and eventually they sort of collapse. But again, in the collapse state, we have sort of a closed pack structure. You see, this is much closer than the structure which we have seen previously. Okay, and not only by the temperature, but we can also tune this lattice parameter by electric field. Okay, so if we look at this structure and see, I am applying electric field, and you can see the lattice parameter is decreasing. Okay, the particles are coming close. It's almost a compact structure. Okay, therefore, apart from the temperature, we can tune this coronal structure by external electric field. And note that this electric field required is very, very small. Okay, it is 1 or 2 volts. Okay, therefore, it is much smaller field required than any solid crystals we want to make any change in the crystal order. Okay, so what we expect that this is sort of a basic idea of how we can make the tunable crystals. Okay, and the use of tunable crystal is that if we can make a 3-dimensional colloidal crystals, okay, we can design a photonic crystal, or what is called as photonic bandgap materials, which are very, very useful for many applications. In fact, that is the one of the areas to be emerge with time. Okay, a lot of works are going on, but there are new approaches are being thought and also implemented. But I think still that area is evolving. Okay, so what we believe is that introducing topological defects into the particle, we can make 2-dimensional and hopefully the 3-dimensional colloidal structures. Those structures are tunable either by temperature or electric field. And these studies are very, very useful for making tunable photonic colloidal crystals. Okay. Now, let's say if I have the particles with non-spherical particles. Okay. Let's say elongated particles. So these are the silica particles of around 3 micrometer length, but diameter is around 700 nanometer. Okay, this is a sort of a mastic kind of thing. You can see very elongated particles. Now, if you disperse them in liquid crystals, what you see that you can actually guide the assembly of the particles to make a long chain, polymer-like chain. Okay, so each silica particle acts as a monomer, and you can make a silica sort of kind of polymer. Okay, and the particles are bound by strong forces of the liquid crystal media. And this is, if you say this each particle acts as a monomer, therefore it is a homopolymer because the repeating units are the same, therefore this is a homopolymer. Now, if I have a mixture of a rod, this nanorod, and this spherical particle, I can make a copolymer. That means which is AB type. A means A is this sphere and B is the rod. I can repeat this unit AB. N is, it goes to infinity. In principle, I can make a large, colloidal chain of polymers. Okay, and this is AB type polymer. Similarly, we can have microrod. This is nanorod. This is microrod. This is nanorod. This is the sphere. Okay, so this is A, B, C, B type unit. So this unit is repeated. So we can see that even we can make a side chain like this. So we can make a complicated, sort of colloidal chain. Okay, which is analogous to the polymers, the conventional polymers. Okay. Now, if I have a magnetic particle, okay, in this case the particles, for example, are cubic, and the size, the diagonal of the length of the cubic particle is at 2.5 micrometer. This is extremely small particle. Okay, you cannot see them in bare eyes. Now, when you disperse this particle in liquid crystal, we can see they induce some different kind of defects. So what you notice that these cubes, they have different orientation in the liquid crystal depending upon the types of defects they induce. For example, this red line shows that the ring defect. You remember I said that in case of sphere, we have a ring defect. The ring goes around this spherical particle. Since here the particle is this cube, it goes around the this longest diagonal plane. Okay, in this. Now, if this ring sort of escape from this position and go either left or right, it goes to this point. It becomes a point defect, and therefore the crystal rotates. Sometimes it also can sort of get stabilized at one of the edges of these cubes. Okay, and therefore the cube's orientation is different. So depending upon the defects, they have different kind of orientation of the particles in liquid crystal that can give rise to very complicated assembly of magnetic particles. Okay, this is magnetic particle. This is a AT alpha 304. This magnetic particle. Now, so we find a very novel way of measuring this magnetic moment of this particle. Normally, measuring magnetic moment, we take a bulk sample, so thousands of particles are there, and we do a bulk measurement, and we get an average magnetic moment. But I will show you here in this experiment, using a simple concept, the magnetic moment of individual particle, which is 2.5 micrometer, can be found easily. So this is two particles are assembled in liquid crystals. Now what you see, if I apply a magnetic field in this direction, you see this object rotates in the magnetic field direction. So this is the direction they are rotating. You see, they rotate in this direction. So what happens? When you apply the magnetic field, the particle experiences a magnetic torque. Okay, and that is mu b sine phi minus theta. So this is the angle with respect to long axis of this particle and the magnetic field. But since the particles are in an elastic medium like liquid crystal, they also have elastic energy, which is given by 2 pi c k theta square. So c is that parameter connected to the shape of the particle, which we can find out, and k is the average elastic constant, and theta is the rotation angle, which we also can measure from from image. Now, if we take the derivative of this with theta, we get a torque. So we basically balance the elastic torque and the magnetic torque. By equating these two torque, we can calculate the magnetic moment of this each particle, or either of the order of 14 into 10 to the minus 15 ampere meter square. Okay, and this numbers actually is much more accurate as far as single particle is concerned than any bulk measurement. Okay, so therefore this kind of assembly also helps us to measure magnetic moment of the individual particle. Now I will talk about something which is in the previous part. Previously I was talking about the dispersion of spherical or the silica particle in liquid crystals, spherical or rod or cubic. Okay, that was a colloidal suspension. Now I will say I will talk about what happens when you have liquid crystal colloids. Okay, this is basically a kind of emulsion. Okay, so the emulsion is when you disperse one liquid in another immiscible liquid. So we make a tiny liquid crystal droplet and disperse in another liquid. So what we get is we study optical properties, and we get what is called or what we observe is the whispering gallery mode resonance. Let me tell you briefly what is whispering gallery mode resonance. This idea of whispering gallery mode resonance came from the sound resonance of sound wave. In fact, this is the St. Paul Cathedral in London. This is the dome of that. It's very big, of course. And here, a whisper can be heard from any part of this. Okay, big dome. Okay, so now, so this is a big dome, and that means whisper can be heard from any part of this dome. And this theoretical explanation of this whispering gallery mode resonance was first given by Lord Rayleigh in 1910. Okay, so this is basically a resonance of sound wave. In fact, similar thing can be seen in Golgambaj in Bijapur. So now this idea or the concept can be utilized or used in case of liquid crystal droplets. The basic idea is that the whispering gallery mode resonance in optics is that if we have a dielectric sphere, okay, of refractive index N2 and outside medium is N1, if you inject a light here, the light, because of total internal reflection, will keep on rotate, okay, without much loss. So this is several hundreds of cycles will be there without much loss. Okay, therefore, whenever the 2 pi r is the radius, and whenever the light circulates on complete cycles, if that is equal to integral multiple of the wavelength of the light which is injected, then there will be a resonance. This is basically simply a geometrical optics. And this can also be understood based on the Mies-Cattering theory. It suggests that we have the modes of the resonance around this periphery, which is depicted like this. Okay, the basic idea is that if you inject light will be circulating without much loss, and there will be a resonance. Now, this idea is sort of used in liquid crystal displays. So you can see this is sort of a emulsion, and there are tiny droplets, many different, and of course sizes are different droplets in a polymer. This polymer is PDMS, and these liquid crystal droplets are small things what you see here. So before you make this droplet, we disperse an amount of dye, which is shown by the red color here. So I'll tell you why the dyes are needed. So basically these droplets are doped with some amount of dye. Okay, so before you form the droplets, you can dope some dye. Sorry. So yeah. Okay, now this is one of the structure of one of the droplets. The molecules, liquid crystal molecules are radially out. Okay. Now, since they are dye molecule, the dye absorbs some light, which is 532 nanometer, and it gives fluorescence. The moment you excite such a dye, such a droplet, then there is a fluorescence, and the fluorescent light is trapped within the droplet, the circulate, as I sort of have shown here. Now, this is a droplet as seen under optical polarizing microscope. This is perfectly radial. Before you excite, the moment you excite with a 532 laser, at this point, you can see there is a bright light ring around this particle. Please note that the size of this microparticle is around 10 micrometers, extremely small. Okay, and this brightness of this perimeter is coming because of the circulation of light. Okay, this is nice. So now, if you send the light to a spectrometer, you see that we have beautiful whispering gallery mode resonance. We can also find this mode. We can label the modes. You can see they are mostly transverse magnetic modes. Okay, and these modes have very large quality factor, is of the order of 10 to the power 4. Of course, this is much smaller than the solid dielectric, but it is still, it's quite high as far as liquid crystal is concerned. And the beauty of this resonator is that you apply a small external electric field, and you can actually change the quality factor substantially, which is not possible in any solid dielectric microsphere. Okay, therefore, you can have tunable micro-resonators. In fact, now the point is, what happens if you pump more and more energy through these droplets? Then you will see the droplets start actually lasing. I saw you one short video clip. This is liquid crystal droplets. Okay, under optical polarizing microscope, remove the polarizer, you see they're perfectly sphere. The moment you excite with the laser, you can see they glow. Okay, this is because of they have optical resonance. Okay, and the more and more energy is pumped, these particles start actually lasing. Therefore, these using liquid crystal microdroplets, we can make liquid crystals sort of micro resonator as well as micro lasers. Please recall the beauty of such droplets or the resonator is that you can tune them with external electric and magnetic field. They are very sensitive to this any environmental change as well as external fields. Therefore, they can use as micro sensors. Okay, in fact, they are very good sensors. There are a lot of studies on these micro droplets. Now, so to summarize my first part, that I have shown you that by dispersing foreign particles in liquid crystal, we can design complex architecture of these coral crystals. These crystals are actually stabilized by topological defects of the medium as well as the long-range elastic forces of the liquid crystals. And such structures are very, very useful for designing photonic crystals. And on the other case, I have shown that liquid crystal droplets can act as a micro-resonators, and those resonators can be also made to work as a micro lasers, which are tunable. And this kind of micro-resonator, micro lasers are very useful for making soft optical chip, meaning like electronics, you have chip, okay, which is made of solid semiconductor material. You can also make a material sort of soft chip, and which are useful also for biosensing and detection. Okay. Now, in the last part of my talk, I will show you that when you apply external electric field, these particles actually behave like a micro swimmers, mimicking some of the real life living systems. Now, this is a part of the subject called active matters, and as you know, this is one of the emerging areas of physics. So, active matters are basically composed of the particles, larger number of particles, which are active agents. Okay, there are large number of active agents. These agents continuously absorb energy from the medium. Therefore, the medium as a whole is out of equilibrium. Okay, and there are plenty of such systems where you can, which can be sort of found as a active matter. One of the beauties is that they are non-equilibrium. Okay, and one of such simple examples of that is let's say these micro swimmers. These are the examples of two active matters. So here I saw that here I saw some movies of algae. These are chlamydomonas, which you can see in water. You can see they are moving randomly here and there, either because of food, in search of food, or because of reproduction. Okay, and what is important that they have some flagella, and they beat this flagella in the fluid, and therefore create a local flow. The flow is towards the body of the chlamydomonas. Okay, and the arrow shows the direction of the flow. That is how they swim. Now, if you look at that, so therefore, this is the flows are like this, and this kind of flow around the particle is called puller, okay, because it's pulling the fluid towards the body. Now, on the other hand, if you look at the bacteria like E. coli, they are called pushers because they have actually flagella here, but they beat the flagella in the fluid such that they push the fluid out from their body, and that is how they move. And these are called pusher. Okay, the flow direction is away from the body. Now, the point is when you have a large number of such particles, you can see that the collective behavior emerges from this, and physics of this collective behavior is very, very interesting. Okay, a lot of studies are being done. In fact, compared to experiments, theoretically, this subject is well developed than experiment. Now, our question was that can we create? See, doing a controlled experiment on such a living system is not trivial. Okay, it is really complicated matter because it is a living system, and you have to create appropriate environment to study them and do controlled experiments. But now the question is, if I can artificially create such controllable active particles, we can study the collective dynamics, which will be able to mimic the living systems, and a lot of new physics will emerge. So our basic goal was to create artificial microswimmers whose direction of motion can be controlled. As you know, when you put a foreign particles in a solvent like, let's say, water, and if you apply external field, the particles can move due to two reasons. One is called linear electrophoresis or non-linear electrophoresis. If the particles are charged, let's say it's a negatively charged particle, and you drop in some fluid, so they will attract positive charges around there, and since the electric field in this direction, and because of that, these positive charges will move in this direction. There will be local flow, it's called sweep velocity around this particle, and the particle will move in the opposite direction of the field. And this is a typical linear electrophoresis because the velocity of this fluid and the velocity of the particle is essentially proportional to the linearly with the electric field which you apply. Zeta is the zeta potential and eta is the viscosity. Okay. Now this is basically the Helmholtz-Somolsky equation for linear electrophoresis. Now suppose the particle is not charged and you drop them in solvent and apply some external field. Assume the particles are polarizable. Let's say metal particle. Okay. The moment you apply field, since the particle is polarizable, they create a charge separation within the particle that attracts the opposite charges around them. The same charges are now experience the electric field and therefore create a local flow of the fluid around them. And this is what is called nonlinear electrophoresis. That means this particle had inherently zeta potential. Here the zeta potential is created by applying electric field. Therefore, if you put zeta equal to AE, A is the radius of the particle, this becomes E square. Therefore, the flow around the particle is E square. But as long as this flow has this kind of symmetry, fore-aft symmetry, okay, you can see this particle will not move. Though there will be a local flow around there, the particle will not move. Okay. Now the question is, what happens when we disperse the liquid crystal droplets in liquid crystal? Sorry, this particle in liquid crystal. In the first part, I have said that this particle induce different types of defects. For example, this is a particle which inducing a ring defect, which is represented by this black thick line. So this is a quadrupolar particle. Now, when we apply electric field, what happens? There are some impurity charges in the liquid crystal. They cannot pass through this particle, therefore are separated across this. Okay. Now those charges which are collected here experience the same electric field, and we can show that the velocity of this fluid around this particle, which is symmetric, they have fore-aft symmetry, but it depends on the dielectric anisotropy of the liquid crystal, conductivity anisotropy of the liquid crystal, and it varies quadratically with the field. Okay, therefore it is nonlinear electrophoresis. But the point is that such particles having a ring defect or the fore-aft symmetry will not move into the fluid. Okay, and in fact this is the experimental velocity map. Okay, it shows that you have sort of four big symmetric vortices, and therefore this particle will not move. Of course, the particle will be able to move if we break the symmetry of this flow field around them, and this is possible in some cases. I'll show you. Suppose if you have these particles have a boson defect, like they have some surface defects here and there, again the flow is symmetric. You can see the arrow shows this flow of fluid when you apply electric field in this direction. This is a true velocity map. Again, we see there are four vortices. The field is nearly symmetric. Therefore, the particle will not move due to electric field. But if the particles are having point defect here, okay, and you see the flow, the big lines is stronger in this region compared to the behind of this particle. See, this is what you see here. The flow is stronger here compared to the vertices. So four vertices are there, but the symmetry is not there. These particles will be mobile. They will move along either this left side or right side, depending upon where is the point effect, left or right. Okay. So this is called dipolar particle. This particle will be motile in the liquid crystal, but recall that they will have only bidirectional motion, meaning they will either move left or right. And this was reported in long ago by this group of Kent State University. Now, the problem of such thing is that this particle motility cannot be controlled, meaning they are restricted in the x direction only. So, but then question is, if I want to study this active particle, the particles will be able to move in all directions. Then, so our idea is that how we can make steerable or controllable particle. So we design what is called Janus particle. So Janus is a Roman god which has two faces. One sees the future and other sees the past. So we take a spherical silica particle, okay, and then half of the particle we coat with the titanium metal, which is a thin metal of around 30 nanometer, okay, and diameter of the particle is 3 micrometer. So this is basically called metal dielectric Janus particle. You can see the same image. To define contrast tells you that they are metal dielectric particles. Now, when you put these particles in liquid crystals, they induce this ring defect, topological defects in the liquid crystal. Then we apply electric field. So I will show you that. So the particles, this particle having a ring defect like this. Okay, of course you cannot see the defects here. Now when we apply the electric field, we can see that this particles moves. The field is perpendicular to this plane. Okay, and this is the orientation of the liquid crystal molecules. We can see the particle moves facing the dielectric hemisphere. Okay, in the x direction. But if the metal dielectric is up, we can see electric field is same. In all cases, electric field is perpendicular to the plane of this screen, but the director is in the x direction. So this particle goes up. So this particle was going right, this particle is going up. If the metal surface is down, this particle, you see, this is the defect configuration of the particles. Janus particle, it goes down. Okay. Now, if we have the other orientation, for example, metal dielectric interface makes some angle with respect to the director. This is the director. That means this is the structure. So metal dielectric is like this, and this is a ring defect. Ring defect is always present because it is a quadrupolar particle. We see the particle goes diagonally in this direction. Okay, but if you have a metal surface in the other side, particle again goes diagonally, but in the other direction. In this case, if the metal surface is down, it goes diagonally, but downside. In this case, again it goes diagonally, but in the other opposite direction compared to this. So therefore, you can see that the particles in a plane, if you apply an electric field perpendicular to this plane, though the liquid crystal molecules are oriented in the x direction, they can actually go in different directions depending upon how the metal dielectric interface is oriented. Okay. See, therefore, this is not a bidirectional motion. You can see because in a plane it can go in any direction. Now, if you look at the summary, that so if you define a vector, you define one angle phi, and the Janus vector S. The S is perpendicular to the metal dielectric interface, and N is the orientation of liquid crystals in the medium. So if you make an angle phi, by varying phi from 0 to 360 degree, we can get defined orientation of the Janus particle like this. Okay, you see, continuously it is rotating. Now, this shows that this is the trajectories, okay, with time-coded trajectories. So this means red is 0 and blue is the high. So that means the particles can be transported in all directions, okay, in a 2D plane. Therefore, this is the omnidirectional motility or transport of the particle. This is very, very special. You cannot see such kind of motility in any other isotopic solvent like water. Here, we are applying a field perpendicular to this plane, but we are able to guide or transport the particle in all possible directions just by tuning this orientation of the metal dielectric interface. Okay, and this is now we will show that we can also remote control the direction of motion by varying the field. So here in this movie, I will show you that what happens when we change the electric field from 1.5 to 2 volts per micron. Okay, frequency is fixed. So you see, this particle was initially going in this direction. Now I change to 2 volts per micrometer, and recursively between 1.5 and 2. You see, whenever I change the voltage, direction of motion of the particle is changing. Okay, from left to right to left. You see. Okay, so therefore, the direction of motion of the particle can be controlled by changing the field amplitude recursively between two values. Okay, at a fixed frequency. Similarly, we can also remote control the velocity, remote control the direction of motion, fixing the voltage by changing the frequency from 30 to 50 hertz. So here I will show you that this particle was going initially in this direction. I change the frequency from 30 to 50 hertz. See, now it becomes slow, but its direction of motion is changed. okay, towards particle direction. Again, I go back 30. Recursively, I'm just showing that the particle direction of motion can be controlled by just varying the frequency of this applied electric field. So now these things can be sort of used for steering the particle in a at will. For example, I have a target here and I have a particle here. So I choose a particle with appropriate metal dielectric interface and apply electric field by continuously varying the electric field. I want to guide this particle to this location, and you see this movie demonstrate that. See, the particle target is here. See, by amplitude, I'm just continuing the amplitude of the particle and sending the particle to a desired target. Therefore, this is very, very important for targeted delivery in subsystems. Okay. And the question is, how do you understand such kind of utility? Yeah, this I will not go into details of the theory, but let me briefly tell you what actually goes, what is the physics for the motility of such particles. So what do we do? So this is a schematic of this directed field around the particle having quadrupolar symmetry. This red is the line is the ring defect. Now we can, since we are applying electric field in the z direction, we calculate electrostatic force density of this system, which comes out to be this. Where delta epsilon is the dielectric anesthetic of liquid crystals, delta sigma is the conductivity anesthetic of liquid crystals, and these are the Green's functions. And del theta del z is this sort of the change of the angle of the molecular orientation with respect to the z-axis, and this is with respect to the x-axis. So this part is called splay, this part is called bend, and psi 0 is the electric potential of this field sphere, which is given by this, where E0 is the applied electric field. Okay, and the lambda is 1 when it is conductor, lambda is less than 1 when it is dielectric. Why we have to write? Because I have half, this is a metal dielectric interface, we have half dielectric, half metal. Therefore, for metal side it is 1, for dielectric it is less than 1. Now, if we from this analysis, I will not go again into the details. From the force density analysis, we find the electrostatic force in two orthogonal plane, namely that xz plane. So xz plane is this xz plane, okay, and the yz plane is different. For example, in the xz plane, we find that this electrostatic force density is off-centered. They form a force dipole. First of all, the force dipole is off-centered, meaning they are not in the center, but it is off-centered somewhat here. Okay, and in such case, the flow of fluid around the particle is given by these arrows. Okay, that means the flow is towards the particle. It is like the polar type flow, which I have shown in case of chlamydomonas. Okay, but now since this is a metal surface, which is highly polarizable, the electrostatic charge, density of charge is higher, therefore flow is expected to be stronger. Now we can see the symmetry of the flow is broken, being the, I mean that flow is stronger on the left side and the right side, therefore the particle moves facing the dielectric hemisphere. In the other plane, the yz plane, if you imagine this one and you say there is only bend, so that means the director are perpendicular here, but essentially it goes into the plane as you go away from the particle. This bend will give you a force dipole which are opposite, again off-centered. Then in this case, what happens? That means the flow is away from the body of the object. Okay, and these are the basic example of pusher type. And in this case, again, this is the density of ions is, or the density of charges in the metal surface is high because of high polarizability. The particles will move facing the metal hemisphere. Okay, that means the particles in one plane can move in the facing the dielectric hemisphere, or it can move into the facing the metal hemisphere. Okay, now if you look at our summary of the experimental results, I said the particles can be guided to move in all possible directions. That means the particle which is moving facing the dielectric hemisphere is a puller type. Particle which is moving up with a metal hemisphere is a pusher type. That is like your E. coli. This is like your chlamydomonas. But the particle which is made between some angle, this is having both puller and pusher type. That means this is a hybrid particle. So this puller type microswimers, therefore this is like these particles are puller type microswimmer. This is pusher type microswimmer. This is a hybrid microswimmer. Therefore, this is a unique sort of system by just engineering the different structure and orienting the particle, we can actually have puller, pusher, or hybrid type microswimers. Okay. And so the last part of my talk, I would like to summarize is that what I have shown in the last part is that we have created a controllable active particles which acquires motility in the liquid crystal by transmitting the energy of the external electric field, or AC field, which we apply. That means particle as such, it doesn't move. When you apply external electric field, the particles become motile and they consume the electrostatic energy. And what is more important is that we achieve complete command over the trajectory of the particle. That means we can guide this motility of the particle at will, okay, in a 2D plane. Therefore, we believe that actually we have demonstrated sort of a emerging paradigm of topology, which is the abstract concept of mathematics, used to be thought like that, but we can see realize them in experiment, and the property, and which their properties also can be useful for practical applications in complex systems like active matter or even making colloidal assemblies. Okay, so with this, I would like to end here, and thank you for your kind attention. And if you have any questions, I'll be happy to address them. Thank you very much.
Thank you, Professor. It's a wonderful presentation. And you have covered basics of liquid crystal to assembly of nanoparticles in liquid crystals. So it's quite interesting. And if any questions are there, let us take a couple of questions. Participants, if you have any questions, please let us know. If there is no questions, Professor, I have one question, couple of questions. These neutral particles are attracting each other in the liquid crystals, right?
Yes. Yeah. That is very important point. Yes.
So, because like a charged particle, we can call it as a magnetic pulse kind of thing. Right. So, is it due to gradient of director?
Yes. So here, what is happening when you have a uniform orientation of liquid crystals? Okay. Now you put these foreign particles. This particle create elastic deformation, right, in the medium. Okay. That is a director distortion. Okay. Now this medium wants to minimize elastic energy. Okay. Therefore, if you have two particles, it so happens that if you calculate elastic energy, you will see that when two particles are at close proximity, the elastic energy, total elastic energy, is lower than when they are separated. Okay, that is the called elastic force which drives the particle to move and assemble.
Okay, and one more question, Professor. Is anybody try to assemble the liquid crystal droplets in glycerin or some other media using the optical tweezer?
See, there are some studies on the assembly of the droplets, but those are in the quenched sort of emulsions. Okay.
Okay.
But you don't have control. It so happens that if you have a emulsion of liquid crystal droplet and with some many mixtures of different kinds of polymers, and when they quench the system, they found that quench means high to low temperature. They found some sort of regular size of the droplets and assemble over a larger region. Okay, so they are spontaneously formed, but using liquid crystal, yes, not. At least to me, I'm not aware of such studies. But that may be interesting to do that. But it is not trivial because trapping a dielectric sphere using optical tweezer is easier than trapping a droplets in another invisible liquids. Yeah.
Okay. Then assembling the nanoparticles in 8 cb liquid crystal kind of thing, we can detect the phase transitions, right?
Yeah. So you see, when you disperse nanoparticles, the nanoparticles are too small. Okay. If the density of the nanoparticles are low, the nanoparticles are so small. For example, if it is less than 100 nanometer, the nanoparticle does not create substantial amount of elastic deformation around them. Okay. Therefore, the medium as a whole looks like a uniform medium. But if you measure the physical properties, then you will see that physical properties you are getting not because of liquid crystal alone, but it is due to both the nanoparticles and the liquid crystal. Okay. So, but the dispersion you will not see. Like what I see here is when the particles are macroscopic in size, the bigger size, that is visible.
So you have developed two phase transition techniques. So one is due to whispering gallery mode. So another one is due to dispersion of the nanoparticles in the liquid crystal.
Yes. Yes.
Is that correct?
Yeah. So in droplets, you have a phase transition.
Thank you, Professor. Thank you for joining us.
Thank you, Varun. Thank you very much.
Thank you very much. Thank you for accepting our invitation and giving presentation in the conference. Thank you very much, sir.
And
now I request all the participants to join the respective rooms for their presentations.